Hello, I am Dr. S.K. Tiwari. I am from National Resource Center for Earth Sciences, Banaras Hindu University, Varanasi. The course is on Tools, Techniques and Experiments in Earth Science. Today we are going to talk on the various techniques of dating and its implications for correlation. The lecture will be covered in two parts. In the first part, we will talk about the various dating techniques, and in the second part, we will cover the implications of various dating techniques for the correlation purpose. Earlier investigations of Precambrian rocks, that is, older than 540 million years ago, using law of superposition could only produce a relative time scale, according to which rocks higher in a sequence are younger than those below. Further, efforts were made during early 20th century to quantify relative time scale using radiometric dating of rocks in order to formulate an absolute time scale. It was realized early in 20th century that decay of unstable elements to produce radiogenic isotopes could be used to date the minerals and rocks of Earth's surface. However, at that time, analytical techniques were not precise enough to determine the minute quantities of radioactive isotopes which are present in the rocks. So, in 1950s, when mass spectrometer was developed, rock dating became very common. The science of dating rocks in all its aspects is termed as geochronology. Now we'll talk about the fundamental principle of radioactive decay. According to this law, the number of atoms disintegrating per unit time, that is dN by dt, is proportional to the total number of radioactive atoms present. Hence, we get dN by dt is equal to lambda n as equation number 1. Or this can also be written as dN by n is equal to minus lambda dt as equation number 2, where dN by dt represents the number of atoms disintegrating per unit time, while n represents the total number of radioactive atoms present, while the lambda is proportionality factor, which is also termed as decay constant and has a characteristic or a specific value for each radionuclide. It represents the probability that an atom will disintegrate in unit time. On integrating equation 2, using the variable separable method, we can get the equation 3 and 4, where n0 represents the number of radioactive decay at original time t. On integration of equation 2, using variable separable method, we can get the equation 3 and 4, which are integration of dN by n is equal to minus lambda integral of dt plus integral constant, which can also be written as log n to base e is equal to lambda t plus integral constant. Now at t0, that is at time 0, we will get n is equal to n0, where n0 represents the number of radioactive atoms present at original time t. Now using the initial condition, from equation 4 we can get the integral constant c and the value of n and n0 by using equation 5 to 8. Here, equation 9 and 10 forms the basis for calculating geological age from the analytical data, which are n by n0 is equal to E lambda t, or this can also be written as n0 is equal to ne lambda t. Now, using the initial condition from equation 4, we can get the constant of integration c and the value of n and ngo by using equations from 5 to 8. Here equation 9 and 10 forms the basis for calculating a geological age from the analytical data, where n represents the total number of radioactive atoms present, while n0 represents the number of radioactive atoms at some original time. Now, the number of radiogenic daughter atoms, Nd, formed during a period of time t can be given by equation 11 and 12, where The half-life, that is T-half, represents the time required for radioactive atom or a given amount of radionuclide to decay to one-half of its initial value. This half-life is related to decay constant lambda by the equation T-half is equal to 0.693 divided by lambda, that is decay constant. While using equation 11 and 12 of radioactive decay to calculate age of a geological sample from the measured parent-daughter ratio and the appropriate decay constant or half-life, it is essential to remember that the calculated age will yield the time of crystallization or the crystallization of the rocks. But we have to keep in mind that this is possible only if first, if there have been no loss or gain of either daughter or parent nuclide by the processes other than radioactive decay of the parent. Second, the half-life of parent nuclide is accurately known. Third, if precise correction can be made for any daughter nuclide incorporated into mineral or rock at the time of crystallization. Fourth, if mineral or rock was formed in an interval of time that is very short when compared with its actual age. Now, when more than one dating method is applied to a mineral or rock and the resulting dates agree with analytical error, the above conditions are clearly obeyed. Such dates are termed concordant and are found in many rocks which had a relatively simple geological history. However, discordant dates are also frequently found in certain types of geological environment. They can result from the failure of one or more of the above conditions in regions with a more complex geological history. Such discordant age patterns can be extremely useful when several geological events have been superimposed on one another in a single area. The various geological events which can be dated are: number 1, crystallization of igneous rocks from a magma. Second, recrystallization of pre-existing rocks of any type to form metamorphic rocks. Third, the uplift, cooling and erosion of fold mountain chains. Fourth, deposition of a sedimentary rock provided that one or more new minerals are formed during or very soon after sedimentation. Now we'll talk about the various methods of radiometric dating. There are a number of radiometric dating techniques, but the most important radiometric dating methods which are applicable to date the Precambrian rocks are potassium argon method, rubidium strontium method, uranium and lead method, thorium and lead method, and samarium and neodymium method. Now we will talk about various methods one by one. First is potassium argon method. This method is based on the principle of radiogenic decay of parent potassium-40 isotope to daughter argon-40 isotope. The half-life of potassium-40 is about 11,900 million years. Using the equation 11 and 12, a mineral or a rock can be dated very easily by this method. There are several uses and limitations in using this technique for dating of the minerals and rocks. Some of the uses we can discuss here now. The first one is that both minerals and rocks can be dated by this method, which are respectively known as minerals or whole rock dates. Minerals used for dating includes mica, especially biotite and muscovite, and hornblende, and also plesioclase feldspar. There are also some limitations in using this technique. The potassium feldspar, especially orthoclase and microcline, are not very suitable for dating by this method because they can lose organic readily even at atmospheric temperature due to the existence of gross structural defect in crystal lattice and at boundaries between the individual grains. The measured potassium argon dates do not necessarily relate to time of crystallization because diffusive loss of radiogenic argon-40 can occur at temperatures well below those of crystallization of igneous rocks, that is 1200 to 1000 degrees Celsius, and medium to high grade metamorphic crystallization, that is about 800 to 500 degrees Celsius respectively. The blocking temperatures below which different minerals become effectively a closed system to organ diffusion are not known accurately, but are approximately about 150 to 250 degrees Celsius for biotite, 250 to 350 degrees Celsius for muscovite, and about 400 to 450 degrees Celsius for hornblende. Therefore, these measured dates are clearly in the order of biotite less than muscovite, which is less than hornblende, in lower to higher order. Thus, these minerals may become a closed system for organ diffusion at different times because of the respective differences in their blocking temperatures, which relates to various stages in upliftment and cooling history of the rocks. On the other hand, the whole rock potassium organ dating of a lava flow or volcanic ash or a small body of igneous rock in place at higher level in Earth's crust may give true or accurate or actual age of crystallization, because such rock types cooled within a very short time interval compared to their actual age. Further, the potassium organ dates approaching true metamorphism may be obtained from fine-grained metamorphism or metamorphic rocks such as slates and phyllites, which crystallize at lower temperatures such as 300 to 400 degrees Celsius. In case radiogenic organ 40 is incorporated into the rock during its crystallization from outside source, the anomalous or incorrect old potassium organ dates may be obtained. Now we will talk about another method, which is rubidium strontium method. This method is also based on the principle of radiogenic decay of parent isotope rubidium strontium to daughter isotope strontium 87. The decay scheme is given by rubidium 87 to strontium 87. The half-life of rubidium 87 is about 47,000 to 50,000 million years. Besides the radiogenic isotope, which is strontium 87, formed from decay of rubidium 87, the rocks and minerals used for rubidium strontium dating also include common strontium incorporated during crystallization. Thus, equation 11 is to be slightly modified or corrected. It can be written as Nd minus N0 is equal to N multiplied by E lambda T minus 1, or this can also be written as strontium 87 minus strontium not 87 incorporated is equal to rubidium 87 multiplied by E lambda T minus 1 as equation 14, where the strontium 87 represents the total number of atoms of this isotope in a unit weight in a mineral or rock at present, whereas the strontium not 87 incorporated category represents the number of atoms of this isotope that was incorporated into the same unit weight of mineral or rock at the time of formation, whereas the rubidium 87 represents the number of atoms in a unit weight of mineral or rock at present time. And now we can modify equation 14 by dividing each term by the number of strontium 86 atoms, which is constant because this isotope is stable and not produced by the decay of a naturally occurring isotope of another element. And thus we can get equation 15. Now equation 15 is clearly an equation of a straight line of the type y is equal to mx plus b, where y by x represents axis, while m represents slope and b represents intercept. The equation 15 can also be solved for knowing the time, that is, we can calculate the age by using equation 16. In rubidium strontium dating, we analyze several minerals from the same rock. Again, I am repeating the same statement that in rubidium strontium dating, we analyze several minerals from the same rock, or we analyze several whole rock specimens from a particular body of rock. Interpretation and expression of these by a graphical method based on equation 15 is also termed as an isochron plot. Like other methods, this technique has its own importance or uses and limitations. This method can be very easily used to date common rock forming minerals such as mica, particularly muscovite and biotite, potassium feldspar, particularly orthoclase and microclase. But hornblende is not suitable for dating by this technique because of its low rubidium content in its lattice, while gluconite is useful for dating the sedimentary rocks. This technique can also be carried out on whole rock specimens, particularly such igneous and metamorphic rocks which are rich in potassium feldspar and mica, such as granite, granodiorite, tonalite, and granitic gneisses, etc. Basic igneous and metamorphic rocks are usually not suitable for dating by this technique. As in the case of argon 40, as we have seen in potassium argon method, the radiogenic strontium 87 can also diffuse out of lattice at temperatures well below those of igneous and metamorphic rock crystallization. The blocking temperatures for diffusion of radiogenic strontium 87 are in the range of 200 to 500 degrees Celsius, depending upon type of mineral, and it is in the order of potassium feldspar more than muscovite, which is more than biotite. This is the frequent order which is observed for the measured dates in large bodies of granites or gneisses in orogenic bales of the world, which underwent slow uplift or cooling after crystallization. Thus, the rubidium strontium mineral dates records either the time or subsequent metamorphism or the time of cooling and radiogenic closure after metamorphism in the order of minerals blocking temperatures for radiogenic strontium 87. On the other hand, the whole rock age of granite or granite gneiss, for which large samples are needed, the size should be of 10 to 20 kg in weight. They can remain a closed system with regard to radiogenic strontium 87 as well as for common strontium and rubidium. Thus, the whole rock dates of these rocks may correspond to age of metamorphism or magmatic crystallization. The figure 1 here represents an isochron plot for a hypothetical granite sample and minerals present in it. Here the basic requirement for successful application of isochron method is the availability of minerals and rocks with considerable or significant range of rubidium-strontium ratio. The slope of isochron is proportional to the age of rocks, whereas the intercept gives isotopic ratio strontium 87 by strontium 86 of the common strontium when the rock crystallized. We can refer this from the equation 15. In this case, it is to be assumed that rubidium and strontium isotopes did not diffuse from the minerals. Now, it has become possible to differentiate or distinguish two different events using isochron method, as has been shown in figure 2, where the whole rock samples of granite and minerals plot along two separate isochron curves corresponding to 1650 plus minus 35 million year and 1384 plus minus 20 million year respectively. Therefore, we may say that 1650 million year age correspond to original crystallization of granite and 1384 million year isochron may be taken as age of later metamorphism, during which an isotopic exchange might have occurred on a small scale between the minerals. Further, the calculated value of strontium 87 by strontium 86 ratio, which is usually referred as initial strontium isotope ratio, is an important parameter for the study of ultimate origin of igneous rock and source of magma. Further, the calculated value of strontium 87-86 ratio, which is usually referred as initial strontium isotope ratio, is an important parameter for the study of ultimate origin of igneous rocks and source of magma. Now, we will talk about another method, which is uranium lead and thorium lead method. We all are aware that the ordinary lead has 4 naturally occurring isotopes: lead 208, lead 207, lead 206 and lead 204. The first 3 are the products of decay of uranium and thorium, while the lead 204 is not radiogenic and this isotope is entirely non-radiogenic. Therefore, it is treated as a stable reference isotope and is used to correct for common lead components, as we have already discussed for analogous case of rubidium strontium by the isochron methods. This method, like the earlier ones, is also based on the radioactive decay of parent U-38 isotope, uranium-235 isotope and thorium-232 isotope to the daughter lead-206 isotope, lead-207 isotope and lead-208 isotopes. The decay schemes are as shown below. The half-life of uranium-238 isotope is 4,500 million years, while the half-life of uranium-235 is about 713 million years, while the half-life of uranium-232 is about 13,900 million years. The isochron equations for various isotopes of uranium have been shown in the equations from 17 to 19, where the uranium-238 isotope decays into lead-206 isotope, while the uranium-235 isotope decays into lead-207 isotope and the thorium-232 isotope decays into lead-208, where lambda-1, lambda-2 and lambda-3 are decay constants of uranium-238, uranium-235 and thorium-232 respectively. Now, the equations 17 to 19 can also be solved for calculation of time. The equations 17 to 19 can be used to plot isochron graphically in a similar way as that of rubidium strontium isochron, as has been shown in figure 2, where slope of isochron is proportional to the age of rods. In general, these methods have a much more restricted range of application than potassium-argon method and rubidium strontium methods, because they are used to date rare minerals in which uranium and thorium are major constituents. However, very frequently these methods are applicable for minerals such as zircon, sphene and monazite. In some cases, uranium-238 lead-206 ratio and uranium-235 and lead-207. However, very frequently these dates are applied to minerals such as zircon, sphene and monazite. In some cases, the ratio of 238 to lead-206 and the ratio of uranium-235 to lead-207 dates for a mineral is found to be concordant. Often, the discordant dates are obtained which result due to lack of a closed system behavior. Example, loss of lead during metamorphic events after crystallization. Very useful geological information may be obtained from such discordant age patterns, particularly from zircon, as exemplified by the Concordia-Discordia diagram as shown in figure 3. When the ratio of U38 to lead-206 and the ratio uranium-235 to lead-207 dates for a given rock are same, they are said to be concordant or concordant dates. If the ratio lead-206 to uranium-238 and the ratio lead-207 to uranium-235 are plotted against each other, the concordant samples of various ages define a simple curve which is known as concordia. However, the above mentioned ratio in zircon defines a chord that intersects concordia at 1725 million years at the upper part and 65 million years at the lower part as shown in the figure. The zircon edges are referred here as discordant, as the chord upon which they fall is a line of lead loss or uranium gain. The upper intersection with concordia is generally interpreted as initial age of formation of zircons, that is the crystallization of granite. The lower intercept gives the age of the later thermal events that resulted in lead loss. Now we will talk about another new technique which is known as sensitive high resolution ion microprobe technique. This technique has been developed to analyze the above mentioned ratios. Through this technique, the polished single crystal thin section of zircon can be analyzed, and dates of the detrital core or core from metasedimentary rocks and euhedral ring can be obtained from Concordia and Discordia plots, or the detrital core and the later thermal event or the euhedral ring. Now we'll talk about another method which is known as samarium-neodymium method. This method again is based on the radiogenic decay of parent isotope samarium-147 to daughter isotope neodymium-143. The decay equation is samarium-147 decays to neodymium-143 isotope. The half-life of samarium-147 is about 10 to the power 10 years. The standard isochron expression is again similar to the rubidium-strontium method as shown in the equation 15, and this can be written as given in the equation 21 and 22. As we know that both samarium and neodymium are rare earth elements, they are not fractioned or separated from each other like rubidium and strontium, and hence the range of samarium-neodymium ratio is much smaller in comparison to rubidium-strontium range in isochron plot as shown in the figure. This lack of samarium-neodymium fractionation or separation is also applied to secondary geological processes such as alteration and metamorphism, and hence the samarium-neodymium dating method has its own advantage over rubidium-strontium method, that it can see through secondary events to primary igneous events. Further, because samarium-neodymium ratio is generally high in mafic and ultramafic rocks in comparison to felsic rocks, the samarium-neodymium method provides a very accurate method of dating mafic and ultramafic rocks. Now here is an assignment for you. Here the assignment is related to the application of different technique methods of radiometric dating to Precambrian rocks. Now let us assume a terrain, the geological section of which is shown in figure 5. It consists of different rock types of different ages A, B, C, D, E and F with different field relations. And the radiometric dates have been obtained which include the ages from A to F. So, from the geological section, the relative age of the different sequences are in the order A more than B, which is more than C, which is more than D, which is more than E, and which is again more than F. So now, on the basis of radiometric data, we have to suggest the absolute ages of A, B, C, D, E, and F. Now we'll talk about application of techniques of radiometric dating for various purposes. The multiple techniques of radiometric dating helps in subdividing the Precambrians, which are the older ones. The table 1 gives radiometric data from a hypothetical terrain consisting of granite gneiss intruded by a lead granite. The lead granites contain genoliths of older gneisses. The radiometric data shows discordant age pattern produced in rocks formed from 2100 million years ago, which underwent later metamorphism and partial recrystallization 1350 million years ago. Now we can say that the new developments in recognizing and interpreting discordant age patterns have greatly advanced the frontiers of geochronology. In many Precambrian belts throughout the world, the geological history extending up to thousands or several millions of years have been elucidated by the study of discordant age patterns. So with the application of techniques of radiometric dating, the Precambrian chronostratigraphy have been developed more precisely. The table 2 shows the subdivision of chronostratigraphy, where the Precambrians have been divided into Archean Proterozoic, which have been again divided into early, middle and late Archeans, while the Proterozoics have been divided into early, middle and late with their respective different ages. Again, with the help of radiometric dating techniques, the standard time scale for Precambrian chronostratigraphy have been developed. They have been divided into several eons like Azoic, Archaeozoic, Cryptozoic and Eon, which have been further divided into Erathams and Era, and which have been again divided into early, lower and middle one. They have been further divided into system and period, which have been further subdivided into early, lower and middle, late, upper categories. These systems and periods have again been divided into series and epochs. In the table, the chronostratigraphy of India has been correlated with the chronostratigraphy of North America and Europe, just to make you understand the concept of application of radiometric dating and the development of time scale with the help of such type of dating techniques. So with the help of various or multiple type of dating techniques, we can develop a standard time scale for the Precambrians, and we can correlate the Precambrian chronostratigraphy of various places. So now, with this, we'd like to thank you and have a nice time.